Speaker, Armand Bernou, to use Armand, who's visiting us for weeks, and he's in Portugal at Sapienza University in Roma. And he works in genetic models and stochastic homogenization. And Armand is going to speak about the limit for the beginning of the particle system. Cumulants.
Thanks for the introduction, and thanks a lot for the invitation. It's a great pleasure for me to be here in Chile. Unfortunately, I cannot do this seminar in Spanish. I apologize for that. So yeah, we'll talk about the particle system that at the limit converges to the Maxwell-Vazov equation. But here, what I want to present is some work that is ongoing work, almost finished, with Mitia Duerinckx, who is at the University de Bruxelles. And the question is, what happens if you want to be a bit more precise when you're taking the mean field limit and keep some extra corrections? And what can you do in this case? So I'm going to start with a particle system that is set on the torus because I want to be in the easiest framework possible. I don't want to consider any confinement potential. I don't want to consider any sort of boundary conditions or anything. And so I have n particles, and basically my particle number y receives n interacts with all the particles and receive a force of order 1 over n from each of the other particles. So that's the mean field. And every one of my particles is subject to also a Brownian motion that will disturb a little bit the trajectory. Okay. And so, of course, the interesting object is the interaction here, and I will be a bit more precise about what it is in a minute. But basically, I want to be in the case where I can do everything in the most easiest way. So we will see my hypothesis on B are going to be very strong. And as is usual in this kind of setting, I want to start with IID initial distribution. Okay. Okay. And so I have this system of particles of size n, and what I expect is that at the limit when the number of particles becomes very, very large, I expect each of those particles to be described by a limit SDE, which is going to be nonlinear, which is the Maxwell of SD. And in this SD is basically the same thing as before, except that I replace what was the empirical measure here by the law of the process itself. Okay. So this is a probabilistic way to write it, and there is also a PDE way to write this, which is to consider the flow of marginal law. And this is just saying, okay, I have this limit dynamics in which when I start with a certain distribution here, I can predict exactly what will be my distribution at time t according to this nonlinear evolution. Here again, you see the nonlinearity because you have this m multiplied by this b, which will itself, you will see, be linear in m, and so you have something quadratic here in terms of the m that you make. Okay, and you can justify this nonlinear PDE at least distributionally. So it gives you a way to translate sort of the probabilistic setting to the PDE. Okay. So now let me be a little bit more precise about the kind of interaction that I'm looking at. So typically, I want to look at what is called H-stable potential. So first, my B is going to be linear in the measure argument in this sense. I will have a sort of parallel force just in front, but I will just put it at 1. The only important thing here is that it cannot be negative. I cannot look at attractive settings in the work that I'm going to do. It's just going to be a repulsive step. And I have this gradient of W. And the W is going to be very nice. It's going to be smooth, coordinate-wise even. But in particular, it will have some very good properties for the limit equation. And those properties, you can see them as encoded in the Fourier coefficients of the W. So this is a work of Carillo, Valani, Paviotti, Schlichting. And basically, when you have something for which all the Fourier coefficients are non-negative, then you have some nice property for the PDE, which is that the Lebesgue measure on the torus is going to be the unique invariant measure. And that is going to be exponentially stable in the sense that if I'm starting with my limit flow, if I'm starting from any distribution and I let it evolve around some time, it will converge exponentially fast towards this Lebesgue measure on the torus. Okay. So when I said at the beginning that I was going to take the most easy B in some sense, it's what I mean. It's that I take it with this interaction potential, which is really nice. It has these good properties for the limit equation, and that is going to to facilitate a lot more work. Okay, so now let me be a bit more precise about what I want to do. So what I can do at the level of the particle system is I can write a density for my particle system, and then I can write what is called in this setting a Kolmogorov equation, but you can think of it as a UV equation. Okay, and so it's quite easy to see it. It's more or less what you have at the limit for the nonlinear RPG, except that, of course, here you have kept all the variables, you have one less integration. Anyway, if you start from the particle system, it's quite easy to see that the density, the overall density of the whole system is going to satisfy this equation. And now, one way to understand this limit behavior as n goes to infinity is to look at the first margin. So what is the first marginal? Is just I integrate this overall density over the last n-1 variable, let's say. Okay, so I do that. And of course, if I do this, it's completely transparent. What happened here, I can just put all the integral inside. So okay, here the same thing. And here, everyone is going to be worth 0 except for the divergence of x1. And in this case, I can just put the integral inside and I end up with this. Okay, and the moral of the story is that I have an equation for my first marginal that chooses the second marginal. Okay, so it's not closed at this level. Okay, now one way to see the propagation of chaos is to say, okay, if my two particle marginal, this Fn2 here, was exactly the tensorization of Fn1 and Fn1, I will be done. Okay, because I will end up exactly with this, which is the PD formulation of my limit equation. And one way to say that is that, okay, my Fn2 is equal to Fn1 tensorized with itself plus a correction. And this correction is exactly the two particle correlation. Okay. And so one way to justify the propagation of chaos is just to say the two particle correlation goes to 0 as n goes to infinity. Okay.
Just a simple thing, the gradient of W, why disappears? Why it gives you like this Bx?
No, it's just because the form of B, sorry. So the form of B is this, but with kappa equal 1. And so basically, I use interchangeably the gradient of W or the B form. It just depends. But okay.
Okay, that's why it's B. Yeah. Okay, thank you.
Okay, and so physically, at least when you're looking at the right sort of weak norm, you expect this two particle correlation to be of order 1 over n. Okay, and so indeed it converges to 0 as it goes to infinity. Okay, but the question that I want to ask is, what if now I have a fixed n that I know is large, and I want a correction to the mean field limit? I want a correction. I want to keep the term of order 1 over n. Then I can rewrite the limit equation with using this this extra correction here. So I write n Gn2 so that this is of order 1, but I have the 1 over n term. Okay. So now I have an equation for Fn1, which is corrected and which is accurate up to the order 1 over n. But of course, it's not closed, because now in this Fn1, I have this Gn2, and I don't know the dynamics of it. Okay. But what I can do is that I can start from here and now integrate over the last n-2 variables. And this will give me the equation for Fn2. And in this equation for Fn2, I will have Fn3, okay, of course. But now Fn3, I can say again, okay, these are tensorization of Fn1 with Fn1 and Fn1, Fn1 and Fn2, and so on, and the three particles correlation Gn3. Now let me assume that I know that Gn3 is of order 1 over n squared, that is I'm willing to throw it away. Now I can write an equation for Fn2. It's going to be horrible, I'm sorry. But the point is, I have this equation for Fn2 with many terms that are just, okay, tensorization of Fn1 and of Fn1 and Fn2. But at the end, this equation for Fn2, if I'm willing to just put all the terms of order 1 over n squared here, because I know that the three particle correlation is of order 1 over n squared, it only uses Fn2 and Fn1 everywhere. Okay, and I have terms in this that are order 1, I have terms that are order 1 over n, sorry, but that's all. And so since my Gn2 is nothing but Fn2 minus Fn1 tensorized twice, if I'm willing to throw away this term, I have a description that is accurate at the order 1 over n, and which is a system of two equations that is closed. I have Fn1 here, Fn2 here, and so I'm able to compute everything. Okay, and also I know the initial data because remember I took my initial particles to be IIG, and so I know that my Fn2 at time 0 is nothing but Fn1 tensorized twice, and my Gn2 at time 0 is like 0. Okay. Okay, so the goal of of course, I've done it, for Gn2 and Gn3, but of course, if I wanted some correction to the 1 over n squared, I can do even more equations and get some even more closed forms. But the thing is, I have to control those things, those correlations. So, yeah, so my goal is just to have this, okay, I will say it again in a minute, but it's just to have the sort of controls for every order of particle correlation. Okay. So let me sort of give you a 3-slide review of propagation of chaos. So in general, the idea is that, okay, first let's start with a finite time. And one way to prove the propagation of chaos on finite time is just to say, okay, if I have my particles at the beginning, I want to show that they weakly converge towards IID copies of the solution of the limit equation, the mathematical equation. So this gives both the convergence towards the limit equation and also some asymptotic independence. And so this is an old problem that comes back to, let's say, Smith coupling that shows that for the same sort of setting that I'm looking at now. Also, it was revisited quite recently by Lacker. And there are other approaches that are based on the tightness. But the important thing is that, of course, and especially you see it here because it's a compactness argument for this thing, so it's qualitative, it's not quantitative at all. Okay. Okay, now the next step is what about if you want some quantitative steps, and then I will divide into strong errors and weak errors. And strong errors are about the convergence in the Wasserstein norm. So typically, the sort of things that you want is to compare the law of your I particles with the law of the limit equation. And so if you're in a Wasserstein distance, then you want to show, for example, that's of order 1/n squared. Sorry, that is and the key question for the sort of estimates is also that you want to be able to derive the limit equation without any condition on the time. And so you want uniform in time estimates for the propagation of chaos, which is also the important thing. So in this toroidal setting that I'm looking at, you have some results that are uniform in time for this sort of strong norm. For example, if the potential is of the same form that I took, but with W convex, then you have a paper of Madrigal and that almost 20 years ago now. You also have some papers doing this for small interactions that will actually also fall in the setting here, but I won't detail it. And of course, then you have the question of what happens if the interaction kernels are quite singular, okay, which is a very active topic. And so you have results for Delarue and Tse that are uniform in time, but you have also a very important paper by Jabba Wang, quite recent, which gives non-uniform in time results, but people have worked quite hard to transform the sort of results that they had into stuff that are uniform in time.
So just something that shocks me is the fact that you have like the uniformity in time up to infinity.
Yeah, just
why is like usually you get like uniformity on compact?
No, usually you okay. If you can't do something uniform in time, you just result you take it on compact interval so that okay you can just upper bound by the worst time in some sense. But what you really want here is to avoid this issue and to be able to say.
And what's the intuition why it works for uniformity in time? Why don't you get like sometimes where things behave?
Okay, again. So okay, in general, I think it will depend on the interaction, but one of the main things to remember in this case is that the Brownian will actually help. They will provide some kind of mixing and that will help. For instance, if you look at the same kind of systems without the Brownian motion, then you definitely, I don't think you get something really.
Okay. Okay, so no, so the main idea is somehow also that is the law, no? So you don't have a coupling that is uniform in time in a way. You have you don't have a coupling of the paths that are uniform over time. You just have like for a fixed time the distance in the process is that doesn't matter. Just.
Okay, I have to think some more. I'm not sure.
It is not decreasing in time.
So it's decreasing, but it's you have to control that.
So if it decreasing in time, is that?
Yeah.
It should be a flux.
Yeah, but this is where the noise really comes in. It's which is kind of fall into this stuff. Okay. Okay, so those are strong approaches, and here I want to take a slightly different path, which is to consider weak errors instead. And weak errors are going to be like comparison of what happens for the empirical distribution or for the limit dynamics when I use some function that acts on measure. Okay, let's say a test function like that. So there have been some approaches around this. So cases where phi is polynomial, phi is linear. So okay, you might think it's real here because the linear case comes after the polynomial case, but the interactions were not the same, which is explains the thing. But usually what happens is that those approaches gives you a rate of order 1/n, especially for stuff that can be quite singular, but those are not uniform in time. Okay. And now one of the starting point of our work with Mitia is a recent result of Delarue and Tse, which is exactly in our setting, basically, where they obtain this uniform in time convergence of this weak error. Okay. Yes. Okay, and for me, it's again, I want to prove in some weak sense that my correlations will stay uniformly in time of order, okay, my n+1 particle correlation will stay uniformly in time of order 1/n to the n. And so if you look at n = 1, it's basically controlling the two particles correlation. So it's basically the same result as this one. Okay, it's just a propagation of curve result. But I want to show you that, okay, basically what I will do is I will show it again, that if you take n = 1, things work and you get some uniform control in time. But with different tools, and I hope to convince you that these tools can be leveraged so that you can also control the higher order correlation with the same sort of thing. Okay, so for that I will have to use cumulants. So, okay, I think probably you're familiar with this, but cumulants is just a way to measure on sort of the interactions between random variables. And okay, I will use mainly the second cumulant, which is exactly the variance, and the third cumulant, which is exactly the skewness. But it's not general. I mean, the fourth cumulant is not exactly the kurtosis. You have some extra corrections that comes. Okay. And so our main result is that if I'm looking at a test function that has this form, so it's basically using this char phi, and then it's linear in the measure argument. If I'm looking at the n+1 cumulant of my empirical distribution, of phi of my empirical distribution here, uniformly in time, I get something which is of order C/n to the n. Okay, and let me sort of justify this fact that we use the cumulants of phi of mu n t, at least for the variance, in a very, very formal way. If you look at the variance of phi of mu n t, then, okay, I can write it on the board. Okay, so obviously you got the expectation of this thing squared, but because of the linearity, you can say that this is 1/n squared sum of yg. And on the other end, you have the expectation of this thing to the square, and by linearity and by extendability, this is just e of phi of y1t to the square. Okay, and then you see that here, basically you have two cases, either y or j are different, and in this case, it's exactly this thing. It's exactly as if you're looking at y1 and y2, because the numeration doesn't play a special role. And if the two are the same, then you end up with phi of y1 square again, and then you have to compare this phi y1 square with the expectation of phi y1 to the square. And so if you split things correctly, you end up with this. But what's important is that, okay, if I'm willing to neglect this term because it seems to be of order 1/n, whereas the rest is of order 1, then I end up with this thing. And if I write this thing in terms of the marginal, let's say, then I indeed get f2 minus f1, which is exactly g2. Okay, so it's a sort of justification of why I'm looking at those cumulants here. All right, so how will it work? Basically, in this problem, you have two sources of randomness. You have the Brownian motions on the one hand, and you have the initial distribution on the other hand. And I really want to split the way I will treat the problem between the sources of randomness. So I will write, for example, the expectation, the variance, and the cumulants without subscript when it's global. And then when I condition, and then I'm looking at only one side of the randomness, let's say the initial data, I will put a little subscript 0, and when it's Brownian, a little subscript. Okay. And for example, for the variance, what does it say? So, okay, I'll go for the variance to show that it's of order 1/n. Okay. And what does it say here is that the global variance is a variance with respect to the initial distribution of the Brownian expectation and the expectation with respect to the initial distribution of the Brownian variance. Okay. Okay. Actually, let me write this down. Okay, and of course, you can do this for any cumulants. You have what is called the law of joint cumulants that allows you to do the same kind of tricks, even if you're looking at the third order cumulants or the fourth order. And to show that the overall thing is of order 1 over n, I will just show that each term individually is of order 1 over n. Okay. And in particular, I will show directly that the Brownian variance is of order 1 over n. So I will be done. And this thing I will have to do a little bit more trickery. Okay. And so typically, what is the kind of tools that we will use? Here, it's tools that are coming mostly, I mean, from mean-fit game theory. So it's expansion in the versus time space. Okay, and then we have to combine with some nice algebraic estimates. I will be more precise by that. And this is inspired by the whole machinery of Delarue and Delarue and Tse and so on. And then to compute things that are related to the initial distribution, we rely on sensitivity calculus in the sense of Glauber. And this is something that Mitia introduced for the case where you don't have noise. And just to sort of answer the question from before, so if you're looking at the system without noise, you're able to make exactly the same sort of derivation for the cumulants, but now they're not uniform. You're able again to control and to show that, for example, the second cumulant is of order 1 over n, but you have an expectation, an exponential of time that is somewhere. Okay. Okay, so now I will focus on those things, the Brownian parts, and I will add only after what happens with respect to the initial distribution. Okay, so my first goal is to show that actually, if I'm looking at the n+1 Brownian cumulant, it's already of order 1 over n to the n. Okay, and this is a uniform in time estimation. Okay, so for instance, for my variance, it will be enough this will be enough to show that my Brownian variance is exactly of order 1 over n. But in general, it's not enough at all. If you look at this sort of decomposition for the fourth order cumulants, you will have the variance with respect to the initial distribution of the variance with respect to the Brownian motion. And so if you only know that this thing is of order 1 over n, it's not at all enough for something that you expect to be of order 1 over n to the cube. Okay. Okay. To sort of make those computations, that I will have to use the linear derivative. And this is just, okay, I have a function which is which takes a measure, a probability measure on the torus as an argument. And I just want to be able to write a Taylor's formula with integral reminder when I'm looking at f evaluated at one measure versus f evaluated at another measure. And basically, I define an object that does exactly that. So this will do it, except that it will take an extra argument, a punctual argument, and this argument will be integrated between in the differences between the two measures. Okay. So basically, is that if you want to define an object that represents this difference in such a way that you have a Taylor's formula with integral reminder, this is the way to do it. This is the more. So, okay, and of course, okay, this is just because you have the difference and those two have the same mass. This is just defined up to a constant, so you have to put an additional condition. Okay. So this is the notion of linear derivative that I will use, and there is a relative notion that I will also use, which is the one of Wasserstein derivative. And actually, in this setting, it has a nice interpretation, which is just that here you have a dependency in this punctual argument, and so the Wasserstein derivative is just what you get if you make an additional derivative in this y. Here, okay, so the Wasserstein derivative is just the derivative with respect to the punctual argument of the initial the linear derivative. Okay. So there are a clear dictionary between the two notions, which can be made much more precise than what I sketched here, which is in the books of Armand and Delarue. And one other thing is that this object is itself depending on the measure argument. So of course we can look at what happens when you do the difference between those two two objects like this with measure arguments, and so you can define higher order derivatives as well. Okay. Okay.
I want just for an idea. Well, in principle, that derivative is a function. So in some sense, I don't know if it's I mean, it's a function of the measure of the point where we are taking the derivative and of the point.
Yeah.
Because it's kind of you're using as a dual for the measures. You're using the primal, which is the bounded functions or continued functions, something like that.
So it's a weak derivative.
Yeah, it's kind of a weak derivative in some.
It's a weak Fresher derivative. Okay, so now what is the nice thing about those derivatives is that, okay, let me take my test function and evaluate it along the flow. So I start with the measure, I let it evolve along the limit flow, and then I evaluate the end function phi, okay, that I'm interested in. And actually, you can write a PDE for this quantity you phi t mu, and you can write the PDE by using those notions of linear derivative and Wasserstein derivative. Okay, so they will allow you to write a PDE for the time evolution of this object. Okay. And why so nice is because now if I look at the Brownian expectation of my phi of mu and t, I can write it, of course, as if I were starting with my mu and t as the initial distribution and let it evolve for no time along the evolution. And now what is this? This is a random variable inside that depends on all my position at time t, y1t, ynT, okay? So now I can do an Ito formula. And if I do an Ito formula, of course, I will have the time derivative of this u phi somewhere. And this time derivative, because I have this master equation, I will be able to detail exactly what it is and to see some compensations with the other terms that are coming from my other terms in the Ito formula. Okay. And so when I do that, there's something really nice that appears, which is that the Brownian expectation of this function of mu and t is expressed as something that only depends on the initial distribution that I let evolve along the limit flow, plus something of order 1 over n. Okay, so I'm saying that, okay, at the first I had something of the empirical distribution at time t. Now it's a function only of, now it's decomposed as something that only depends on the empirical distribution at time 0 using the limit flow, plus a correction that is exactly of order 1 over n. Okay, and okay, in this correction there is the form is a bit awful. You have this Wasserstein derivative coming in and so on. But okay, still it's interesting because it tells you exactly what is the term of order 1, what is the term of order 1 over n. And actually, this again depends on mu and s here. And so you can do the same trick. You can say, okay, now I have a new functions that depends again on measure. I can do the exact same trick. I can push the expansion even further. And now what I get is exactly the term of order 1, which depends only on mu and 0 pushed along the limit flow. Again, the term of order 1 over n, now it's only depending on mu and 0 pushed along the flow, but with a more complicated function, and exactly the term of order 1 over n squared.
Just a technical question. Why do you know that this integral is not blowing up as a power of n? So it gives.
No, it's actually you have some. Okay, I will say something about it just after, because also this is the key point to say that, for example, this thing is uniformly in term of order 1 over n, and same thing here, it's uniformly in term of order 1 over n. So we say something about this in a minute. Yeah, actually, this is my next my next slide. Yeah. So okay, let's just say that I know that this integral. Let's say that I'm able to show that this integral is of order 1 uniformly in time, and I have something of order 1, something of order 1 over n uniformly in time, and let's just say that I know that this thing is of order 1 uniformly in time, and I have something of order exactly 1 over n squared uniformly. And of course, I could push this expansion even further to get more decomposition, let's say, of this. Okay. And okay, actually that's the point, but it's quite technical, so I won't be too much precise about it. But the thing is, when you have those sort of derivatives with respect to the measure, and even if you then derive a bit with respect to the punctual arguments here, you can actually represent. So remember, my u phi is defined from my phi. Okay, my phi itself is a function of measure, so it admits linear derivative as well. And so I can define the object, basically the objects that appear here. For example, here, I can define them as just taking the measure argument of my initial function that I wanted to evaluate at. And then the punctual argument I evaluated at some weird distributions here. And those weird distributions, okay, they are awful, but they're basically linearization of the limit equation, of the limit flow. Okay. And in particular, okay, they quickly have a very sort of very long form, and okay, it's complicated to write, but actually the structure is quite simple. And you're able to do some ergodic estimates for the structure. So for example, here I wrote D1, which is, I think, the first linearization that you get if you just take something in the limit nonlinear equation and you just perturb by a little bit and you look at what the linearized equation that comes at it, you get this. And then you're able to show that this thing, if you're willing to go into very weak norms, you will have exponential decay, basically. And so this justifies the question from before, is that I will be able to represent this thing as stuff that will decay exponentially fast here. And so if we go here, then this means that this object would basically be of order exponential minus t minus s. And then you integrate it in time, so you get something of order 1. Okay. And this also justifies why you can again take where you can again push the extension for this object because you know it's well defined. Okay. Yeah. So this is quite technical, but just the moral of the story is that you're able to control everything that appears in the extension that you're doing, and to show that they are indeed uniform in time, as you say. Okay. And so now let me write this. So I first push. I use the previous decomposition, and so I get this thing that depends only on mu and 0 pushed along the flow. Okay, there's something of order 1 over n. Now I can do the same with the test function, which is phi squared instead of phi. And then I will get the same thing, but with u phi squared here. Okay. And so when now let me take that to the square. This will be to the square. And the only terms of order 1 is just u phi of t mu and 0 to the square. And then everything else is of order 1 over n at least. Okay. So I want to compare those two to compute the variance. But of course, the only thing that remains is here, this u pi square, and this is u phi to the square. But u pi square is nothing like phi square evaluated along, you take mu and 0, evaluated along the flow. And so you end up with exactly this one. And so those two cancels. And this tells you that the Brownian variance is exactly of order 1 over n, because, okay, the only terms of order 1, they cancel each other. Okay. And actually, you can play the same game for every Brownian cumulant that you want to compute. We have those sort of cancellations. They get more and more hard to see because, okay, they will involve harder objects, but you will always see these polynomial cancellations get up. Okay, and so erase here. Okay, so here I have that this object is already of order 1 over n. So in this sense, this thing is done, it's of order 1 over n. Okay, and this one, I know that it's exactly 5 of nt mu and 0 by the expansion that I did, plus something of order 1. And now I have to show that when I take the variance with respect to the initial distribution of this object, I will end up with something of order 1 over n, which is not clear at first sight. Okay, and for this, I will use Glauber calculus. So in a sense, what I told you is what happens for the things inside, which are just related to the randomness with respect to the Brownian motion. And now I want to tell you how do I handle the randomness with respect to the initial distribution. Okay. Okay, so the idea of Glauber calculus is the following: is imagine you have a functions of the n initial particles. Okay, the K Glauber derivative will tell you how this function deviates between the realization that actually happened and the mean realization of the K variable in there. Okay, and so typically, if I take a function of the mu and 0, this is just going to be my function evaluated at mu and 0. And what happens if I replace the K variable with 1 over n dz, where the dz is distributed according to mu 0. Okay, is that clear? Yeah. So, okay. But now the next thing is that here I have something which is a function of a measure. Here I have something which is a function with respect to a measure. And I have the differences between two different measures. And so I will see up here the linear derivative. Okay, as before. And so, okay, I have this weird form where again I have some time, I have a complicated measure argument here, okay, but that doesn't really matter. And I have a punctual argument. And the punctual argument is evaluated at the difference between the two measures. But the difference between the two measures is only what happens on the K variable, so it's of order 1 over n. Okay. And once again, I have my arithmetic estimate. So basically, you can think of this as being of order exponential of uniformly something in exponential minus t, let's say. And now you have this, you can split this integral into a sum of two things that are of order 1 over n. And so you see that the K derivative of, okay, of this object, that actually the K derivative of this object is of order 1 over n. And of course, okay, the other one you says, okay, the Glauber derivative is just a sum. So if the term is already of order 1 over n, then I can always say that it will stay of order 1 over n. Okay, I don't know if it's very clear what I said. I'm just saying, okay, here I can really apply a Glauber derivative. Here it's already off order 1 over n, so I can do nothing there. Okay. Okay, and I end up with the fact that the cake derivative of my Brownian expectation of phi mu and t is of order 1 over n. And then I have an F-Einstein inequality that tells me that the global variance with respect to the initial distribution can be controlled with a sum of the square of the Glauber derivative. So I get a sum of terms that are of order 1 over n squared, have n terms in this sum, and so I get something of order 1 over n. Okay. Now, if I want to play the same sort of game with higher order cumulants, we have some, let's say, high order Poincare inequality that allows to do the same sort of tricks. Okay. For example, for the third cumulants, I will have control in terms of those Glauber derivatives in such a way that you will always end up having the right order that you expect. Okay. So all of that was just to, okay, so now it's, so when I put this thing into the machinery of here, I get something of order 1 over n. This is the conclusion of it. Okay, so all of that was just to show you something that was already known, which is the uniform propagation of chaos in time for this setting where, okay, I have this interaction and in the toroidal setting and so on. But, okay, I hope I convinced you quite a bit that the way I did it is a way that can really be adapted to treat any order of correlations. And I will show you it to you with the third cumulant, okay, to just give you an idea of how it works. So now I have this thing, which is the third order cumulants. I want to show that it's of order 1 over n squared. Again, I have this law of joint of total cumulants that tell me that this is this thing, okay? And so now, okay, let me write down. Okay, so what do I have? I have the cumulants with respect to the initial distribution of the Brownian expectation. I have the expectation with respect to the initial distribution of the third Brownian cumulants. And I have something crossed, which is the covariance with respect to the initial distribution of the second Brownian cumulant, which is the variance. And then okay, now I want to show that each of those terms of order 1 over n squared. Okay. So I will have to show, for example, okay, that this one is already of order 1 over n squared. This one, okay, we've seen that it's of order 1 plus a correction of order 1 over n. But now, if I want to apply the same sort of machinery, I will have to be even more precise. So we have to have the exact leading order, the exact term of order 1 over n, and then to say, okay, the rest of it is of order 1 over n squared. Okay. And for this one, there is the same sort of F-Einstein inequality for the covariance. So I will have to have the leading term here, the term of order 1 over n, and here, I know the Brownian variance is of order 1 over n, but I will have to have the exact form of this term of order 1 over n. Okay, so. And then you can apply, okay, once you have a good understanding, once you have explicited all the terms that you need in the Brownian expectation, then you can apply the machinery of the Glauber calculus. Okay. Okay, so what do I say here? Okay, so in the previous computation of the variance, I just looked at the first order term, okay, and I saw that there was a cancellation. But now I want to see what is the leading term for the variance. So for that, I push the expansion for the expectation to the second order, to the 1 over n squared. Okay, I have this explicit form for the 1 over n. I push the expansion for the phi squared to the second order as well. Okay. And as we've seen, okay, the two terms of order 1, when I look at this thing minus this thing squared, the terms of order 1 of this one is just this one to the square. And we've seen that those two cancel. Okay. But now I want to understand what happens for the term of order 1 over n. Okay. Okay, so for this one, it's easy. The term of order 1 over n is just here. And for the second one, is the cross between this one and this one, when I take the square of the whole thing. Okay. So I end up with this thing, and on the other end, the cross between the two, which is this u pi that gets out, and then the integral of it. And then everything else is of order at least 1 over n squared, so I'm satisfied with it. Okay. So now the job is to compare those two to exactly get a nice form for the leading term of order 1 over n of the Brownian part. Okay. But actually, okay, this comes back to far away, to the fact that in this U phi one, if you remember, it was just two Wasserstein derivatives of something, of some function. Okay, and so basically what you're doing is you're comparing what happens when you take two Wasserstein derivative of a function to the squared with two derivatives of the function itself times the function itself. Okay, so this is exactly this. So when you take two Wasserstein derivative of the function to the square, you get on one side you get exactly the function itself times two derivatives of the Wasserstein falling on the function. Now on the other side you get the case where your Wasserstein derivative falls 1/1 on every of the two of those g square, and so you have the Wasserstein derivative, one Wasserstein derivative up to the square. Okay, so this makes sense. And okay, and so now if I look at the term with u phi square, I have this two Wasserstein derivative of this u phi to the square. Now I apply exactly this, so I have this u phi and twice the derivative with u phi, but without the square here. And then I have the extra term, which is when I have the Wasserstein derivative of u phi and all of that to the square. Okay, but the nice thing is that here, if you come back to the definition of u phi, this is okay pushing the initial measure mu n 0 along the flow for a time s and then for a time t minus s. So it's the same thing as pushing it for a time t. Okay, and so this term is exactly this term, and so they will cancel out, and what remains is just some sort of default between this factorization here and the twice derivative of this square is. Okay, which gives you a way to identify exactly. So now I know exactly what is the leading term for the variance is this, and then I have some terms for the 1/n squared. And here I said that I know that it's exactly the leading term because you see it only depends on mu n 0. Okay, I do not choose mu n at time further than 0. Okay. Okay, so this is just to identify the leading term for the variance, and then okay, I can use again my sort of Bernoulli inequality to compute this thing. This is just okay. This is again some Glauber calculus that I won't do, but if you do the extension and take the term for the 1, the term for the 1/n, the term of 1/n square, and then you apply the machinery of the Glauber calculus, you will see that this is for the 1/n square. And the last thing that I want to do is to show you that this is already for the 1/n square, several increments. Okay, and so for that, okay, what is the third cumulant? Is the expectation of x to the cube minus 3 times the expectation of x to the square times exponential of expectation of x plus 2 times the expectation of x, and all of that to the cube. Okay. Okay, you're right. So what I want to compare is what happens when I take as a test function phi cube, and phi square base. Okay, so when I take phi cube, I get up to u phi to the cube, let's say, and then write the arguments, and then I have 1/2n. This u1, which is built from u phi, but for phi cube as a test function, plus something of order 1/n squared. Okay, of course I can do the same for phi. Then I have u phi 1/2n u phi 1. And of course the same with the square. Okay, just so that we have all of them in front of our eyes. Okay. Okay, so let's just look at the first order terms. So here I have 1 times u phi to the cube, then I have minus 3 times u phi times u phi to the squares. Okay, so I'm at minus 2 u phi to the cube. Okay, and then I had plus 2 times u phi to the cube. So it gives me 0. Okay. Now the question is, can I see a cancellation for the terms or for the 1 over n? Okay, and if you write what this is, okay, so the first one you get this. The first one is the coming from here, okay, and you see that this is this one, 1 over 2n and u phi cube. The second one is the cross between, okay, when you have a cross between those two, you have two terms of order 1 over n. You have this one with this one, which is this one actually, okay, and you have this u phi square with the u phi here, u phi 1 here, okay, so this is this one. And then, okay, in the last one, you take this to the cube and you look at the terms of order 1 over n, and this is just this one times this one. I mean, this one squared. Okay, and now formally what I'm going to do is just to look at what happens when I take twice the Wasserstein derivative of the function to the cube, and when I compare it with, okay, the function to the square and 2 Wasserstein derivative of the function itself. Here I have the function once and 2 Wasserstein derivative of the function to the square. And here I have the function to the square and 2 Wasserstein derivative of the function itself. Okay, those two I can actually put them together and you get plus 3 over 2n. So this is why I have plus 3 over 2 s squared d squared u. Okay, I've gathered those two. And then, okay, just a simple computation of derivatives. And you end up with seeing that exactly everyone cancels and you get 0 at the end. Okay. But it's just a small computation that you can give to a second year student to analyze it. Okay. Okay. So I hope that this gives you an idea of how you can actually treat all the correlations for this kind of system and then get this control in this weak form that is when you test again this phi of mu and t to justify some correction to the mean field equation to another 1 over. And the last thing that I want to talk about in just 2 minutes is the case of second order system, because actually you can do exactly the same when you are looking at system in which are kinetic systems. And then, okay, you have a position that evolves according to your velocity, and your velocity it is affected both by the interaction, but which depends on the positions, and by a Brownian motion that is going to be a perturbation. Yeah, sorry, this would be Dirac over xy. Okay. Actually, it's very easy to write this system exactly as the previous one. Okay, you just write it in a vectorized manner, and you just get the same sort of system as before. It's just okay. You have to be a bit careful because now you have a Brownian motion that is twice the dimension, and you want to put a matrix in front of it to cancel the part of the positions. Okay. But basically, what I'm saying is that this system you can write it as the first order system. Provided that you're willing to add a little bit, a little matrix in front of the position. Okay. But actually, okay, and then all the machinery works the same. The only difference is that when I'm trying to represent those linear derivatives that appear when I'm pushing the expansion and so on, there I don't have exactly the same sort of equations because the limit equation is a nonlinear Fokker-Planck equation that is kinetic. No, it's the Glauber-Fokker-Planck equation. And of course, so the linearized version of that will be a linearized kinetic equation. And so the ergodic estimate, you rely on a very different structure, which is a kinetic one. And so you have to use tools that are now quite common for linear kinetic equations, which are hypercoercivity techniques. And those hypercoercivity techniques, they will allow you once again to get those exponential decays. Once you get, if you're willing to go into very weak norms, okay, you will get those. And that's it. And then, okay, it's nice you are able to treat also the second order system. And I think for the second order system, already like propagation of Carrot uniformly in time is quite interesting as well. There are many possible extensions that I mentioned in the beginning. We took a very nice interaction and we took it in the torus. But of course, you might ask, what will happen if I put a confinement potential? Okay, maybe even a very sympathic one, a convex one or something. And what will happen if I go to the whole space? And we expect many tools to carry on. The main thing is that you need the properties that I listed at the beginning that are inherited from the form of an interaction on the nonlinear Fokker-Planck equation. Okay? At the beginning, I said because of my choice of B, the Lebesgue measure on the torus is my unique invariant measure, and it's exponentially stable. Okay, The question now is, if you start to change things like that, you will need the same sort of results, this exponential stability. And also a nice measure on which you can linearize, which is also a key question. Okay, I think I will stop there, and I'll be happy to answer it.
I have a question. Is so what happens if at the start you don't start with IID? Initially, what is left?
The Brownian cumulants probably. You can still perform some analysis. I mean, what am I saying? Yeah, if you start with something which is not IID, you can still say, yeah, you can still do those Brownian expansions. It's just that your mu(n)0 is not going to be as exchangeable and so on as before. And in particular, I don't know what happens here, because here, actually, maybe you can say something. So, okay, the thing when you don't start with IID distribution is that, of course, you lose the exchangeability in some sense. But yeah, you could actually.
But you could work with, I mean, at least the propagation of chaos, you would assume exchangeability, at least for the initial condition, if not independent, at least.
No, but independent exchangeable is essentially the same here, no? Because you condition on the measure that you get, and you will get the result anyhow. So yeah. It is more interesting when you really start with things that are correlated, but in somehow they will forget the correlation, no?
Yeah.
But exchangeability, I think.
Yeah, but probably not. You're not sure if anything's going to work if you don't have exchangeability.
So you say that, so if I understand correctly, if you don't have exchangeability, you will not have a propagation of chaos. So you will not have a long term. I would believe that long term the particles become indistinguishable one from the other, even though at the beginning you can follow them.
Yeah, okay. So one thing that is clear is that you will lose, I guess, the uniformity in time, because depending on the initial data that you take, you can expect some very weird effect.
Yes, but you would expect that this is just at the beginning of time. So somehow you could.
Yeah,
like the day would be.
Yeah, you could say, okay, up to some point, then I'm basically exchangeable, and then I can apply the machinery that tells me that I need some time.
Yes.
But yeah, I mean, I'll be quite confident about the part related to the Brownian stuff. I'll be less confident about the part with Glauber derivative, which I think has to be checked carefully, because there really might be some exchangeability going on here. I'm not sure.
Thank you.
And can you say something? Since you have high order regarding the central limit theorem with respect to the.
Yeah, it's not done, but it's a plan at some point. Yeah, to say something to describe the fluctuations around this.
Okay. Yeah, because okay.
Yeah.
I mean, you also have central limit theorem for the working vessel.
Yeah.
Since you have an additional term, I mean.
No, but you expect to be able to say something about the central limit theorem for both systems because of those correlations. Normally, they will allow you to do that. And actually, okay, in the work that I mentioned that Mitia did with no uniformity in time, he derived the central limit theorem. So it's just yeah. There is a machinery that allows you, if you have those correlations, to go to the central limit theorem.
Yeah, but since you have further terms, if you want, you can quantify that or maybe.
Yeah, probably you can expect to, but I don't know. Yeah. You have a better understanding of correlation than even in the central limit theorem.
Why is it called? This is simple question. Glauber.
I think it was introduced by Glauber, maybe.
But you know in what context, and or
so
because this Poincare discrete Poincare inequality of higher order, or they were used, for instance, by the.
So
The mathematics.
in some sense, it's not unrelated to Malevin calculus. Let's say.
Yeah, it's
Because we have the
it's
sensitivity stuff.
yeah,
But it's a sort of very discrete version of that.
yeah.
But the Glauber,
Okay.
Now with dynamics, don't you?
Yeah,
Changing
changes
things
of
one.
yeah, so which is exactly what you do here, right? You extend the realization with what we would have expected as a mean realization.
Yeah.
So yeah, I guess.
Yeah. Yeah.
So I have, maybe you said it and I didn't get it, but do you have like a scheme for if I want to do the 10th cumulant?
Yeah.
But do you have like one big way to do it, or you have to just go step by step?
No, so okay.
Is there like, I don't know, some meat function thing?
No, so the thing is you sort of have to do it step by step, but actually you can guess, you know what will be, for example, the leading terms of everything. Okay. The thing is, every time you write things like that, okay, you work in terms of joint cumulants. You have those higher order Poincare inequality that just tells you, okay, if I'm capable of identifying all the terms, then I will be able to perform my Glauber calculus. And so I will be able to recover the right orders if I'm able to compute the cumulants and all the leading terms in the cumulants, in the Brownian cumulants explicitly. And actually, you can compute the Brownian cumulants explicitly. It's a bit painful. We had to introduce some graphical representation actually because the computations were getting advanced. But you can actually do it, and it's geometric in some sense. I can try to explain. Okay, so for example, where do I put this? Okay. So, for example, here in the sense that every time you look at the derivative like this, and every time it factorizes well, like this thing, every time you recover the twice derivative of this thing, you know that it's going to be absorbed by another term. And every time you have something crossed, like this this term, this will give you a leading term. Basically, this will give you a term that will remain in the expansion of the Brownian cumulants once you actually write it down. And so with those sort of tools, okay, you do a graphical representation so that things can sort of get understandable. And then you say, okay, if I wanted to put right away the 10th Brownian cumulants, I will be able to do it because of those representations. And then if you know exactly what is the first term, the second term, and so on, in these 10 Brownian cumulants, you're able to apply the Glauber calculus very abstractly. So the answer is yeah, if I want to compute the 25th cumulant, I can do it. It's just quite painful because the computation to find all those explicit terms are difficult, but the machinery is clear.
If you wanted to write a formula where you leave it's gonna be the expectation of this and this thing.
Yeah, if I'm willing to write that the formula that this that the fourth cumulant, the fourth Brownian cumulant, if I'm ready to write something like that, and that I'm able to identify this A, I'm able to identify this B, and I'm able to just apply it.
Makes sense. Thanks.
Okay.
Yeah, something probably unrelated. In the last slide regarding the second order system, yes. This is still on the torus, right? On the position variable? Okay.
On the position variable.
What's it known about the equilibrium distribution, the invariant distribution?
So in this case, where the interaction potential is nice and you're in the torus, it's actually known again that you have this exponential stability and so on. But this is one of the issues. If you were to change just a little bit the interaction potential or to add a confinement and so on for the kinetic case. I mean, what I'm saying here is that if you change things, you have to check it for both. It's not clear at all that that even if you're able to derive some stability property, let's say for the first order system, for the limit equation of the first order system, they would be also there for the second order.
In the position variable in particular, right? It should be uniform, right? If it's in the torus.
Yes, I think so.
And in the velocity variable, what do we know?
I will guess a Maxwellian distribution,
Okay.
but I'm not sure. But I will guess. Or yeah, no, I will guess that actually. So it's done in the paper of Montmarché from 2017, I will say. Where it does really the analysis of the nonlinear equation corresponding to the limit equation for this.
And they proved convergence to it.
Exponential stability, yes. Yeah, and actually, okay. So if you change the interaction, in the Makin-Vazov limit, you can have a sort of very different behavior with bifurcations and so on. And you could expect to be able to do on one branch of the bifurcation, you could do some control of the correlations, let's say. But of course, okay, this is already technical enough so that we haven't touched that yet. We might want to do that.
Okay, so thank you, Armand, for that very nice talk. And if you have further questions, Armand will be here for some days next week. So.
Yes, and for the announcement, for the other announcement, we are going to go for some drinks afterwards. Let's say we are leaving at 5:45.